Good morning, everyone. Welcome to day 4. We are beginning with Raghuram. Okay, thank you. So today I'm going to give you just a few glimpses into what goes by the name of the Lagrange-Heavy machinery. But I'm going to go back to something I've already mentioned and something which showed up in another talk of a certain local calculation. In fact, I want to do this calculation for G2 for p-adic. So today's talk is going to oscillate between a very concrete example and a very general situation, and back to an example, and I'm going to go back and forth. And hopefully, you get something out of it. So I'm going to take two characters, chi1 and chi2. Characters of cross. In a moment, I'll make them unramified, but right now, I need two characters. And I'm going to use this notation chi1 twisted by s to mean chi1 times the p-adic norm on f, normalized absolute value to the power s. I'm going to let is chi1 times chi2 stand for the normalized induction from the Borel of GL2 to GL2, GL2F of the character chi1 twisted by x by 2 cross chi2 twisted by minus s by 2. Normalized induction. This notation is slightly different from another notation. In any case, if I have a function here, so its value on an A, B, 0, D, G is going to be chi1 A, chi2 D. And now I'll account for the s by 2 and minus s by 2. So absolute value of A by D to the s by 2. But then I'm also working with normalized induction, so that's going to become s plus 1. Okay. That's my representation space. For all A, B, 0, D in the Borel, for all G in GL2F. And the standard intertwining operator, I'm going to denote this T, ST standard of S, which goes from IS, chi1 tensor chi2, to I minus S, chi2 tensor chi1. And this intertwining operator is value on an f. It takes a function here, that's a function, and spits out a function which you can formally check lives there. So its value on any g, this the integral f of 0 minus 2, 1, 0, that's the value element times x. This dx is a measure on additive measure on f. I'm going to take dx, normalized dx as that the volume of O to the dx. And then it's an easy exercise, but then the volume of O cross the units is O minus the maximal ideal, but the maximal ideal is the uniformizer times O itself. I'm going to work with normalized absolute value. The value of the uniformizer is Q inverse, 1 over Q. So if the code goes to 1 minus Q. I want to compute this intertwining operator. So I want to show you, this is the simplest case of famous calculation of Lagrange. So I'm going to take chi1 and chi2 run, right? So that is they're trivial on the units. I'm going to take the sort of normalized spherical vector. I'm going to call it F0 here, and the corresponding normalized spherical vector on the other side, I'll call it F0 tilde. So what is F0? This is the normalized spherical. Spherical meaning it's fixed by the maximum compact, which is GL2O, normalized spherical vector. How do I normalize it? Well, keep in mind that GL2F is the Borel and GL2O. I want it to be fixed by GL2O, and I have this equivariance with respect to the Borel. It's not basically completely determined by asking that it takes on the identity of value 1. So this is an intertwining operator. This will take a spherical, any spherical vector here to a spherical vector there. So it will take the spherical vector to, well, some multiple of the spherical vector there. The question is, what is that multiple? That's what we want to compute. So the standard S on F0 is some multiple times F0 tilde, and I want that multiple. So I know that this is normalized spherical value 1 on identity. So to compute that scalar, the scalar then is the value of the operator at 1 identity. So let's do this calculation. So I want to compute the intertwining operator on the spherical vector evaluated at 1. This is, if I use the definition, the integral over F0 of 0 minus 2, 1, 0, 1x 0, 1, and G is the identity variance. Right? And now, if you have to relate GL to calculations to play this game. Okay, so I have this integral. What you do is you take this integral and you break it up as an integral over O and an integral over F minus 1. And the integral outside the integers, I further break it up as a sum going from m going from 1 to infinity of an integral over pi to the minus m O cross. So I integrate sort of ring by ring, depending upon the valuation of elements outside of O.
You just use that the integral over 0 is 0, so like f is f star union 0. Right? You throw out the 0 point.
0 for 1 point is not going to matter.
Yeah.
In any case, that's going to live here.
This one you don't split.
The integrand, now I stated the integral over O. If x is an integral point, this entire thing is in the maximal compact. The value is just 1. So that will pull out, and what remains is this will just become the volume of O. Which is, and my choice of measure is normalized so that I can take the value 1. The volume of O is 1. So the rest of it I have to worry about. So this looks like 1 plus the sum m going from 1 to infinity of pi to the minus m pi and I didn't systematically. So O is the ring of integers and pi O is the maximum variation. And pi to the minus n units of that of the same 0 minus 1 0 and x 0 1. And at this stage, you need to know a particular here to trick. I can never remember. Although I've used it hundreds of times in my life. So 0 minus 1 1 0 1 x 0 1. You rewrite this as x inverse x 1 minus x 0 1 1 0 x inverse. We will verify that. So I'm going to use this in this integrand f of. And then if x is outside of O, X inverse will be in O. So that's an element in GL2O. And F is invariant under that. So that part I will go off. The rest of it is in the Borel. X inverse X, 1 minus X, 0 to 1. And the other thing I don't care about since that's GL2O. Okay. And so now if I use the equivariance, if I use the equivariance property, the defining property of this induced representation, so this now looks like 1 plus some equal to infinity of chi1 of this X inverse chi2 of X. That one disappears, and then you have to worry about the right absolute value. So let me see if I put this right. To the minus of cross chi1 inverse chi2 on pi to the minus m and units. So any one of these chi-j's on pi to the minus m units is just the value at pi to the minus m. Now I'm using unramifiedness. So this one is going to be chi1 chi2 inverse on pi to the minus m. This over m, and then worry about the absolute value. Yes, keep it as an x. A by d becomes x to the minus 2 raised to this power. Absolute value of x raised to minus s plus 1 dx. This is more right. This then becomes 1 plus some m given from 1 to infinity of. Now you can change your variables, but before I change variables, despite of the absolute value x to the minus s plus 1, I'm going to write it as minus s and write this as dx by absolute value, which makes it and if I make the substitution, x is equal to pi to the minus m unit u, and this is I1, I2 inverse pi back to the power m. The absolute value of this x is the absolute value of pi to the minus m. Pi gives me q inverse, and that to the minus m becomes q to the m. And that to the minus s becomes q to the minus ms. The integral over O cross dx by x mod x is just simply becomes du. That has volume, some volume. So what do I get? 1 plus some. I'm going from 1 to infinity. Chi1, chi2 inverse on pi, q to the minus s. This entire power to the m, and this is volume of O cross, which is 1 minus. Well, there is some geometric series. Sum it up. 1 plus the first term is this one itself. So I have chi1, chi2 inverse pi to the minus s. I have that 1 minus q inverse term divided by 1 minus. All in some half plane wherever things converge. It's just doing a formal calculation. And this essentially have this. You add these two. You add this fraction to that number 1, and you will see that this minus will cancel with that. And what will become in the numerator is 1 minus chi1 chi2 inverse pi q to the minus s minus 1 divided by 1 minus chi1 chi2 inverse. Then of course is I'm going to stick in an inverse, make the numerator into the denominator and so on. So this is the same as chi1 chi2 inverse pi q to the minus s inverse divided by 1 minus chi. So minus S minus 1, I write as minus of S plus 1, this inverse. And this by definition is the local L function of chi1, chi2 inverse divided by Ls plus 1.
Clearly, the miracle in all these computations is that if you do the slightest error in volume or anything, you won't get this simplification. Yes. Like always, the result is like a product of linear factor, and I don't know why, like in any possible imaginable setting. And if you don't get the simplification, like the numerator, there wasn't a reason a priori, like if in the numerator there was like something, imagine there was like 2 plus this, and then what would be the numerator, then you certainly made a mistake somewhere.
So this calculation goes back to Gindikin and Karplevich for SL2R. You can do an identical calculation for GL2R, and you'll see the relevant gamma factors showing up. So what we have really done is we just prove the proposition that the standard intertwining operator at S takes the spherical vector here to Ls chi1 chi2 inverse, the local factor divided by Ls plus 1 chi1 chi2 inverse times the spherical vector of S. This is what very beautiful GL2 calculation, as beautiful as it gets. This, so Langland says somewhere that sometime in the late 60s, in some summer, he didn't have much to do. So he tried to do this calculation in all generality. Okay? And that became his Yale notes called Euler products. So now I want to do this setup. So this works. So the Langland's part of Langland-Shahidi is that this works in great generality. So towards that, let me introduce some notations. So this is the second part of the stuff, maybe second section. I want to talk about induced representations and the intertwining operator. In general, so G is going to be the F points of a connected directive algebraic group. I'm going to let P be a maximal parabolic subgroup. I should say F points of a maximal parabolic. P. I'm going to let write its Levy decomposition as MP times NP. M is the Levy quotient. You think of it as a sub if you want, and this is N is the unipotent radical. The Levy normalizes the unipotent radical, and so if I differentiate that, I get an adjoint representation of the Levy on the Lie algebra of the unipotent radical. I'm going to let NP. The modulus character can be nicely written as so delta P on an element in the Levy is you take the adjoint action on the Lie algebra NP, take the determinant of this action, and take the absolute value. So I'm going to let Z and T stand for the center. AP is going to be the maximal split torus. After I go through this notation in all generality, I'll work out an example. A little more complicated than GL2. X upper star of any of these groups is going to be the of any let me simply say like a calligraphic G. It's always going to be G third star. So algebraic group homomorphism from G to GM or F. And so I can look at the character group of AP, I can look at the character group of MP. AP sits inside MP. So I can restrict a character from MP to AP, and that gives me an conclusion of the characters of MP to AP, which if I tensor with, these are all just abelian groups, if I tensor with Q, this is an isomorphism. And so also, therefore, if I tensor by R. So this element delta P can be thought of naturally as an element of the character group tensor R, and so looks at X star AP tensor R. This is sometimes denoted as the real Lie algebra, the dual of the real Lie algebra. I'm going to let capital delta denote the roots of G. I guess I didn't fix. Let me just work with a connected reductive split. Don't really need it most of the time, but with respect to the torus. And I fix a Borel, and so I get a system of positive roots. Talk about a maximal parabolic, before this actually I'll just fix the Borel and then I work only the parabolic subgroups containing a given Borel.
So now like AP, this is also the split torus of G.
No. I mean take GLN and the
AP.
Yeah.
AP,
so take GLN and take a maximal parabolic whose Levy is GLA cross GLB. Then there is a center of GLA and the center of GLB. This becomes AP. Retract.
You say that AP is the maximal split torus of AP.
Sorry. Maximal split torus in the center of it. So once I have positive roots, I have simple roots. And to get hold of this maximal parabolic, I've deleted one simple root. So let alpha p be that the simple root that's deleted. You get simple root corresponding to the parabolic p. This is also kind of the brain of the subject. If you want to do things in generality, it just takes time fixing all your notations. Well, what else? I'm going to let rho p stand for half the sum of positive roots for the parabolic. So what do I mean? It's half the sum of all those positive roots whose root space lives in the unipotent radical of the parabolic. The algebra of the unipotent radical of the parabolic. Add, take such roots. So rho p, you can think of this as an element of, I can restrict. And because of the half, I have to. It's an exercise to see that if I look at 2 rho p on an M, an absolute value, I want one more, I want gamma p to be the fundamental weight. Corresponding to alpha p. So this is completely, it's 1 over the sparing rho alpha or alpha. This is of the time. Rho alpha. Rho p alpha p times 2. So I'm using this sort of standard Lie algebra type notation, an angular bracket of alpha beta. These are like the Scarpa integers. So it's 2 alpha beta by beta beta. It's linear in the first variable. And this is some standard pairing in the group system. Standard while grouping variable pairing in the group system. I also want the Harishchandra map. HP goes from MP to the real algebra AP. So AP star is this, what's called the dual of the real algebra, and AP itself is formed from the character group of AP to R. This is the real algebra. And what is this map? So I take an HP, evaluate it on an element of the Levy. It should be an element of this real algebra. So it takes as an input a character of an algebraic homomorphism of AP to F star. And I need a real number. So the real number is defined as the exponential of this. Exponential of this pairing is by definition chi for all chi, which lives in X star AP, but identified inside X star AP tensor Q or AP tensor R, and therefore X star MP tensor R. So this is pretty makes sense.
Can you explain what's G there? G of alpha?
Which one?
G of alpha.
Oh, the root space G alpha is the root space. Is the eigenspace for the character alpha, root space for alpha. Something, if you think of GLN, something in the, if I take my root as EI minus EJ, some standard notation, it's the ijth coordinate.
And the last column you were writing, can you read aloud with the top line explicitly? The final column you wrote. Right there, yeah. What's
HP?
HP. Okay.
HP, this is called the Harishchandra map. H for Harishchandra.
And they go from capital MP to frac AP.
Right.
Okay, good.
It goes from the Levy quotient to the real algebra of the central split, maximal central split torus of the domain. And an analogous exercise is the exponential of rho p on HPM is delta p m to the half. You see this when you do your normalized parabolic induction, you have some delta p to the half. The absolute value of a by d to the half. The s came from, I threw it into the twisting character, and it's the half. That's what that's. Okay, I'm almost done. And I take nu. So now I need my inducing data. Maybe phi is going to be an irreducible, admissible representation of MP, and nu is going to be an element of AP star tensor C. So this is the way representation theorists work with induced representations, and one writes I nu P, I nu pi to be the induction from P to G of pi tensor exponential, the same exponential nu HPM, HP as a character on M, and you make it trivial on the unipotent radical. Trivial on the unipotent radical. These are the induced representations. So what does this mean a little concretely? If I want to write this induced representation, I just write it down as what is it as a function. Maybe I'll still leave that up here.
They're kind of hard to read.
Yeah.
Can you write the definition of the next word?
All of that.
No, just the
Yeah, sure. Actually, I don't even need the general view. And this is part of, I want you to appreciate one very delicate point. This is part of Leibniz's genius, that he got this right. Working, his virtuosity in working in a very general setup and introducing the complex variable S just so, okay? If you didn't have it just so, you don't get the right factors here. So
going back to your formula for you're really not going to use the induced representation?
I'm going. Okay. Not for mu in general, but for a particular.
There's 3 tensor factors. And can you just?
I'll just write.
Okay. Yeah, thank you.
I'm going
to. I don't mean to.
No. You take the representation, inducing representation, which is fixed, and then you take a character on the levy, which is going to have this parameter nu, and that character is expressed in terms of this Harish-Chandra function, HP. So its input is an m here, and then using this nu, it gives me a scalar.
So far, the pi is a representation of the levy. And then twisting it by a character.
That's
and
right.
then inflating it
To p. Yeah.
Okay.
So that's the standard thing that you do in parabolic induction.
Yeah, sure. That is so.
Where you put the 1 in?
That's the inflation.
It goes without.
It's the trigger.
It goes without saying. But the exponent is on. Now I'm confused. It's on m or it's on n?
On m. HP is a character on M. It's a homomorphism from MP to somewhere else, and then you pair it with some other object, which is in the dual of that somewhere else, and then you get some state. And for S, a complex number, you go to like mu S as S divided by rho P alpha P. So it's really S times the fundamental weight corresponding to that deleted root. So this is how you introduce the complex variable S in your inducing data. This works locally, globally. This feels like, that I might be brewing heavy weather here, but in my work with hardware, it actually stumbled us for more than 6 months because of not having appreciated how delicately the complex variable S is introduced into the scene. Okay, and so IS pi is going to be this previous one with this mu S. Mu S, mu sub S, not a mu S as versus an old S. Anyway, so what does the function here look like? So in F, there's a function in this, a vector in this induced representation is a function on the ambient group, taking values in the representation space of the inducing representation, such that F of M and G is pi to the M, well, pi of M, delta P M to the half. That half is the normalized part of the induction, plus the way the complex variable S is introduced, S divided by 2 rho P alpha P times F. So this equation is that equation. Just to compare. And now for the intertwining operator.
What you're trying to create is some kind of reducibility condition. Like you want to create a character that for some specific value of S, when you use, you want to create a representation, a family of representations of M, such that for some specific value of S, this induction will become reducible, right? So if you don't do it carefully, probably you're not having such a point at all.
No, I mean, if I replace this S by say 15S, or something, then that point will correspondingly change. It's not so much for.
No, I'm saying not just the S. If you just, like don't put the correct this whole thing, the delta P, like
if you don't put this correctly, this calculation giving the general version of this theorem will not work properly.
Right.
Because in this calculation, there's a very sort of layered induction procedure where you reduce it down to rank 1 operators. And that all those things potentially to break down if you didn't have this S just so. There exists a unique element in the while group, I'm going to denote this W0, which has the property that it takes all the simple roots except the one that you delete. So I take all the simple roots except the one I've deleted to get the parabolic P. It keeps it positive and important plus simple, and takes the deleted root to the negative root. So then this subset of simple roots. So then this subset of simple roots is also the set of all simple roots minus some other simple root that you delete, which I'm going to denote alpha sub q, where so alpha sub q corresponds to parabolic q, maximum parabolic that's associated. And then this property also tells me that W naught conjugates levy to the levy of Q. And the standard intertwining operator, PSTS, takes IS pi to I minus S of the conjugated representation, W. The W naught pi has an obvious meaning. Its value on MQ is you unconjugate via W and then evaluate on. And this operator is given by the same integral. This is the integral for the unipotent radical of the associate parabolic. On F evaluated at G is the integral for NQ, F of W naught and G. And this is the integral which for GL2 which we computed. This was that.
For GL2 it was the upper Borel.
Yes. Yeah. So for G is GL2. Q was on this. And this W naught is at 0 minus 1. All my parabolics are standard. So they're all containing the.
I don't get it. How in those you just associate like this? Just for it.
So now I'm almost there to state Langlands' theorem. Before that, some little more notation. LG is the Langlands dual group, or really a connected component of that. So LG0 is this is a complex reductive algebraic group, which is, this is the Langlands dual. Its root datum is given by you flip the rows of roots and co-roots of G, and there is a unique complex reductive group whose root datum is this dualized root datum. In any case, in this kind of a talk, you may not get what this is. You just need to know it in examples, and after this, I'm going to work through another example. And for this parabolic P, there is a corresponding LP is the parabolic subgroup inside this LG. Parabolic subgroup of LG corresponding to P. It has its own Levy decomposition, LMP circle, LNP. And so the LMP circle acts on the unipotent radical by conjugation. And so I get an adjoint representation of this on the Lie algebra of that unipotent radical. And it's an observation of Langland's. And here, Langland's worked through a certain laborious calculation, and then he showed this to Titz, and Titz showed him how to organize the thoughts using this representation. And this led Langland's to consider the dual group and so on. So what you're seeing at the moment is at the heart of the Langland's program, at the heart of the origins of the Langland's program. So this LLP decomposes as a multiplicity-free direct sum of irreducible representations of LNP. We want to denote this as LNP is R1 to Rm. Rj acts on Vj, which is a sub of LNP, and this Vj, there is a Vj is what is this called? It's spanned. So it's the sum of those root spaces corresponding to some beta, so that with respect to the fundamental weight gamma p beta evaluates to J.
The name of the variable you're bringing into the checksum.
Just give me 1 second. R. It's a cursive R. Okay. And to so recall, pi is the representation, is an irreducible representation of MP. Now let me assume pi is unramified. So far, you've seen that definition for JLM type groups. There's some general definition of it needs to have a fixed vector under a certain kind of maximal compact, some hyperspectral maximal compact. Then you get its Satake parameter, which for GLN was this diagonal n by n complex matrix. Here, the Satake parameter is an element of the dual torus. And you define local lineless L factor as LS by any representation R, GL or some representation of the GL group. This is exactly what you see for GLN and other stars. 1 minus R of theta phi, which is now a matrix there, Q to the minus S, the determinant of this. That's the general local Langland's L factors. And then Langland's big theorem. This summertime calculation on it when you had nothing else to do, as it says, is that the standard intertwining operator on the spherical vector this side is some multiple of the spherical vector on the other side, and that multiple is a product J going from 1 to M of LJS by RJ divided by LJS plus 1 by RJ. This is a scalar which goes up times. And we saw a proof of this for GL2. So Langland's had some way of writing this down, and Titz showed him that this seems to be related to finite dimensional representation of some other group. And then Langland's tried to think about what Titz was actually telling him, and that gave rise to him defining the dual group. Now I want to show you show you an example, a little more non-trivial than GL2. I don't know what it is. Yeah, I'm going to take off that one. Keep all this here. Any questions?
The highest states of the RT are in the.
Yes. Yeah. Here's an example. In the interest of time, I'm going to be skipping some details that I have noted on. I recently wrote an article on intertwining operators of p-adic groups. This example is there in that, so you can look up my paper. It's good. It's there on the homepage. It's going to appear in the Canadian Journal. Arithmetic of intertwining operators of p-adic groups or something. So I'm going to take G as SP2N. I need to define SP2N. So this, for any M, J sub M is going to be my matrix which has ones on the other diagonal, and SP2M is a set of all G and GL2N. So that transpose G, JN minus JN, G. That's my symplectic group. And then if you work through, the fixed the torus, the diagonals of the torus, and you work out the root system, you'll see this big diagram. Diagram of type C. I'm going to delete that root from a parabolic. And so the levy has a Dicken diagram which now looks like a type AN. The levy then is going to be a set of all H. The other transpose H inverse, where H is an element of GLN. If I put a bracket TH, this is, some people call this the other transpose. I heard this in talk of Arthur, using this other transpose. What's the other transpose? The other transpose is, you take the usual transpose and you conjugate it by J. It is, what is the usual transpose? If this is my matrix, you have this diagonal and you flip with respect to this diagonal. The other transpose, you take the other diagonal and you take the mirror image. So that's what it works on. What is not clear? It's an element of GLN. H is in GLN, and this is a block diagonal.
Oh, brackets around the transpose.
Yes. This is in fact Arthur's intuition. The unipotent radical of the parabolic, the Lie algebra of that is 0, 0, 0, x, where x is an element of MM, and it's symmetric with respect to the other transpose. These are all little exercises you can go back home and work out. Rho P, this how the sum of positive roots of parabolic P works out to n plus 1 by 2 times T1 plus Tn. Pj is my notation. I get P1 notation. So on any diagonal, P1 through P whatever spits out the J coordinate. The gamma P, the fundamental weight, I divide by that 1 over rho P alpha P. Rho P alpha P turns out to be this number. So gamma P then comes out the sum of the first 10 coordinates, diagonal coordinates. The Langland's dual group, or the connected component of the Langland's dual group, if G is SP2N, back, this is SO2N plus 1C. This is all elements in SL2N plus 1, satisfying, say, transpose G, J2N plus 1, G. the dual of this, the dual of GLNF is GLNC, and the way it sits, the dual LMP circle is going to be a copy of GLNC, sitting as H1, the other transpose H inverse, H in GLN. And the dual, the Lie algebra of the dual, Lie algebra of the unipotent radical of LP is, this is what I really want, all such matrices, 0, Y, X, 0, 0, minus transpose by J, 0, 0, 0. The various zeros have various sizes, where this Y is an element of, is a column matrix. And X is a n by n matrix, which is skew symmetric with respect to the other transpose. And then this GLN, this LMP circle acts adjoint on this Lie algebra. And then you see that this copy of Y, this is going to be V1, and this copy of X, this is going to be V2. In the sense that LNP, V1 directs on V2. V1, this is just columns, and this is the standard representation of GLN. And V2 turns out to be the exterior square. GLNC. So this is R1, that's R2. And in this example, this calculation of Langlands, then in this example, so when G is SP2M, MP is GLN. I take pi and ramified reducible representation of GLN. Then the standard intertwining operator at S on the spherical vector. So the shape of this formula looks like the standard L function times the exterior square L function at 2S divided by L1 plus S pi, L1 plus 2S times the unramified vector on the other side. This is the shape of it. So I just went ahead asserting many things. In this example, you can sit down and get a big cup of coffee and you can start working it out. Pretty much what I did when I was writing this section with examples in that part. So I was supposed to introduce Langlands-Shahidi L functions. I have talked about the Langlands as part of the Langlands-Shahidi machinery. I don't know, can I take 5 more minutes? Or I can wind up now, or I can take 5 or 10 more minutes. We started 5 minutes. We started 5 minutes late. Okay, so that gives me 6 minutes more. Okay, let's see what. I'm going to very quickly show you what the global theory looks like. Again, I'm just going to put on one diagram.
Can I just ask a conceptual question? You're talking about the method, and I'm not sure what the method is used for still.
I will comment on that too. Go on.
But so you have an equation like this, and my question is the purpose to calculate somehow to calculate the constant appearing, or is the purpose to realize the L factors as arising from an intertwining operator on some smoothness law representations?
Maybe both.
Okay.
The ultimate purpose is, well, there seems to be all these new, this is just the local part of the story, all these new global Euler products. That's what I'm headed towards. Okay. So it's not just the sort of GL2 related L functions that we have kind of talked about, or Rankin-Selberg. There is an entire family. You want to look into this reference. This book by Shahidi, which appeared in 2010, called Eisenstein series and automorphic functions. There are 3 appendices. Put together, there are 58 families of these L functions. In some sense, this is the largest, one method which gives all these various L functions.
It's a collection or it's a monograph?
This is a book.
Yeah, a collection of articles? Or
no. This is a culmination of his 30 years of work developing this theory. So just a briefest of glimpse into the global theory. Let me not write. Here's a briefest of glimpses into the global theory. So just like I had a local induced representation, you can carry out an analogous construction for a global induced representation. You induce from PA to GA of a cuspidal automorphic representation pi, and the complex variable S has been introduced using this fundamental weight, Bare bones, so these are the representation space consists of functions on GA with values in the representation space of pi, but pi is cuspidal on NP. So its representation space itself is a space of cusp forms, and then you can sort of reinterpret the vectors here and think of them as literally functions of some kind. I'll just loosely say C infinity on GA mod PQ. Once you have functions on GA mod PQ, you want to think in terms of the Eisenstein summation and get yourself functions, automorphic forms on G. So this Eisenstein summation, ISP takes the function f, evaluated on a G. There's a sum gamma running over GQ mod PQ of f of gamma G. And once I have this, have automorphic forms, there's another, you can take the constant term, I'm going to denote this f sub q. Q will be directly going to work with the associate parabolic, or you can really take the constant term with respect to any parabolic. This takes a, let's say, an automorphic form phi, and you have seen this integral NQ mod NQ q of phi NG here. Or maybe let me take a constant term, and you'll end up with functions. You're messed with respect to the equivariance with respect to all of G. So this now will be functions on GA mod Q, rational points of Q. And there's this partner induced representation QA to GA of the minus S with the conjugated representation. This is here. And there's a standard intertwining operator, the global standard intertwining operator, which is a tensor product of local standard intertwining. And locally, almost everywhere things are unramified. So you get all these local factors almost everywhere and kind of piece them together. And this, you have to worry about a whole lot of things. For the Eisenstein summation, you have to worry about its analytic continuation. I have some infinite sum here, and there is a complex variable S, which has been introduced, where that converges. And Langlands showed, this is also part of Langlands, the same order product, that if you take the constant term of the Eisenstein series of F, this is basically the standard intertwining operator. So in a sense, this diagonal commutes. This was in the late 60s, early 70s. And then Shahidi went to the institute as a postdoc, and Langlands told him to look at the non-constant term. So stick in a character chi, and if I have a character chi, psi, additive character psi, then I look at this. This is called the non-constant term. And for this to be non-zero, my inducing representation better be something with a Whittaker model. And so Shahidi then spent a couple of decades understanding the non-constant term. In the constant term, which is basically up to commuting of this diagram, you see ratios of the functions. In the non-constant term, it's a little complicated for me to write down this kind of a summary. So for constant term, you see ratios of functions. And if I had non-constant terms, then you actually just see L functions. You just see this much actually in the denominator. Yeah, just what you see in the numerator, but it appears in the denominator. It's a different calculation. You have to compute the non-constant term, the Fourier coefficient of an Eisenstein series. This is what you're doing. Not A1.
Typically, like think of term Q expansions. I mean, you want to clear like something that appears everywhere, and then you get like algebraic. So you're saying that when you do the non-constant term, it gets reversed, like whatever was in the numerator goes to the denominator.
Something like that.
What GLP, what would you find for GLP to do the non-constant term?
I haven't made the sentence precise, so right now just take it for the flavor of things. You just see one, you just see this much.
It's in the denominator. Yeah. Those L factors also have inverses in them. But somehow you see just polynomials,
something like that,
without any inverses. And so that looks like 1 plus L to the K. I mean, is that what you meant by like?
Could be. I don't know about the detail myself, but yeah.
Oh, that's remarkable. So.
Just a briefest glimpse into, I'm done with the giving you a glimpse for the global theory. Yes.
One wants to, somebody wants to read that. That's in the Shahidi's book.
Shahidi's book, silence. Let me just throw a few examples of a group, a parabolic, a Levy, and the corresponding L function, just to kind of wind up everything, and then I get done. The mother of all groups, of course, is GLN. If I take the Deacon diagram of GLN, something like this, and I delete one of them, then the Levy is really a GL and another GL. GLN or GLN prime. Here the corresponding L function that you see, and this was there in Nadelstock. You see the Rankin-Selberg L function of pi on GLN, pi prime on GLN prime. And in the first GL2 calculation I did, you saw that chi1, chi2 inverse came up, right? So the second one is GLS. If I already showed you symplectic, let me take an orthogonal group. Deliberately going to take this. And even orthogonal group of some size. The Deacon diagram is like that. Suppose I delete this guy, then it's a smaller Deacon diagram of the same type. The Levy is O2n plus JL1. And then you get here the degree 2n L function. So if I take a representation pi of O2n and a character chi, you get what's called a standard L function of O2n district by 5. Slightly jazzed up example. If I have a quadratic extension E over F and it gives me a unitary group, let me look at U and N. The Deacon diagram is like this. With the Galois action identifying, the top half with the bottom half. And if I delete that guy, these two are identified now. So the Levy really looks like GLN over the quadratic extension, or restriction from E to F of GLN E. And you can kind of jazz up the situation a little. I can look at unitary groups with similitude, in which case the Levy becomes this cross the GL1. So if I take a representation pi, say a Hilbert modular form, and a character chi for the base field, Then here you get what's called the ASI L function. LS ASI I. That's not a good notation, but. And I put down these three examples just to tell you that. So my work in the last 10 to 15 years has been to study arithmetic properties of these kind of functions. It's this business of Einstein cohomology where this diagram has to get interpreted in cohomology as maps between cohomology groups, and one can prove rationality results for these kind of functions. And I've worked in these contexts. This Rankin-Selberg is my work with Arda, where we had a totally real field. And then recently I have a preprint where the situation is a totally imaginary based field, where the story is quite different. This is my work with Chandrasheel Bhagwat at ISF Union, where we studied Eisenstein cohomology for even orthogonal groups, and we proved a theorem for. You see, this includes part of Shimura. If I take Rankin-Selberg for GL2 cross GL2, GL2 cross GL2 is like an O4. And here, it's ongoing work with Muthu Krishnamurthy at Iowa, myself here, working on the special values of ASI functions. Everything totally real. Totally Imaginary is a preprint I put up on the archives last week, where there are lots of very beautiful, intricate, new, interesting details which I showed now. Okay, so this was just advertising my work. I'm done. Sorry for going over. Up for questions. If you
What was the relation with the data structure?
Oh, he showed a lot of details in this context. The Rankin-Selberg, GLN, if you induce, then you get this. He talked about induced representations and
what story you told seemed a little bit different from what Nadir was saying, right?
Because I did on a very concrete GL2 example and a very general situation, and Nadir was somewhere in between. Huh? Closer to GL2.
What does it mean? Like what you said for this general group, if we apply it to GLN for GLN, we find whatever you wrote there is supposed to be related to what Nadir was saying yesterday.
Yes. So if you work out that GL2 calculation I started this lecture with, but for GLN, inducing from a parabolic maximal, then you will see LS pi cross pi prime dual divided by LS plus 1 pi cross pi prime dual. This is what you will solve this.
I have a nice question.
No, please.
What are the variety results that you get for special values? There are also others that you can get with other representations of the same function. For example,
no. In fact,
yeah, they're different.
This is back to GLN cross GLN prime for special values. In general, it's not known. The only general result which is known is the work of Harder and myself. Unless GLN and GLN n minus 1, you worked in that one special. If m is n minus 1, then there is a beautiful paper of Kajdan, Mazur, and Schmidt in Kreller, where they talked about how the Rankin-Selberg, classical Rankin-Selberg function can be seen in cohomology for trivial coefficients. And then Schmidt has had the student Mankov, and then another student Yanushevsky, myself. So we developed the GLN cross GLN minus 1 story, but that's special. GLN, and if you say GL4 and GL cross GL13, no other method is known other than what we did for special values. And for even orthogonal, this is certainly other than O4 being related to GL2 cross GL2. From O6 onwards, this is new.
And for ASI?
For ASI, so interestingly, when this is the imaginary quadratic extension of Q, some work is there, but all in the GL2 kind of situation. GLN and totally real is again new words. I think no other method we know so far gives special values.
I might have two questions, but I'll start with just one. In your third lecture, you talked about how to extract the algebraicity of the special values of, I guess, just like a standard L function for an automorphic representation on GLN or maybe GL2 even from this cohomology of locally symmetric spaces.
Right.
The rationality results you're referring to showing up from these L functions that arise from these things. Do you apply this cohomological machinery still, or are the rationality results obtained from different methods?
Very much we apply cohomological machinery. In my book with Harder, sorry, anyone wants to look this up, this is, it appeared in the Annals of Math Studies last year or maybe 2 years ago now, volume 203. You will see a diagram of this kind. And the next page, you will see the corresponding diagram with the cohomological interpretation. So this has a diagram of objects and arrows. Here will be the cohomology of a locally symmetric space for G. The induced representations. Now, this locally symmetric space is not compact. There are various compactifications available. What we work with is what's called the Borel-Serre compactification. For every parabolic, there's a piece of the boundary of the Borel-Serre compactification. So these induced representations contribute to a piece of the boundary cohomology. Correspondingly, this contributes to a piece of the boundary cohomology. And then there's an old observation of it's Borel, Harder, and people around them, which says that this constant term map in cohomology corresponds to the restriction map from global cohomology to the cohomology of the boundary. So there is an interpretation, a cohomological interpretation of this diagram. You have to put that together. The constant term map, constant term of an Eisenstein series is the standard intertwining, which has in it the information of L functions. This being a restriction map in cohomology is rationally defined, and that one exploits to prove rationality results of ratios of L functions. So this is, I've basically summarized to you this book with Harder.
Maybe either some students have questions, otherwise I can.
Yeah, in describing this diagram you wrote last time, where I think that John was mentioning, where you do go from or where you get rationality about the results from like the fact that these maps are defined like rationally, like where I guess what is the roadblock in like these other situations, like if you're trying to follow a method like that? I mean, obviously there's probably a lot of details.
There are lots of exactly. There are so I in some sense.
Is there like some fundamental roadblock that one really has to
This is sort of my personal research program, which is you identify various subproblems which you have to solve. These are, if you will, the roadblocks. One is when you work with cohomology, you have to worry about what degree, cohomology, what degree, and then which map. So for example, in the GL2, GL1, I pulled back from GL2 to GL1, and that's basically a line, which is a one-dimensional space. Cusp forms are contributing to cohomology in degree 1. So that degree 1 and that dimension of the one-dimensional is the same 1, and somehow that had to match up. Here, it gets far more intricate. One has to worry about this induced representation contributes to cohomology in which degree, and correspondingly, which degree here. And
so do you need to play this game with like varying the weights a lot, or like the
there is some wild group combinatorics which comes in. So there is a beautiful paper of Costant in the Annals in the 60s, where he computed. It's a classic actually. Take an algebraic group G, and take a parabolic P with Levy NP. If I take any irreducible representation pi lambda v lambda. Algebraic, everything algebraic, finite dimensional representation with highest weight lambda, then Costant computed the cohomology. I can think of this as a G module, but let me think of it as an MP module and ask what is, in fact, he worked with the Lie algebra. what is this Lie algebra cohomology group? And there's a beautiful answer to this. Turns out that there's a sum over certain elements in the while group, which now people call constant representatives, of V W dot lambda. That's the twisted action of the while group on weights. And I take the extreme finite dimensional representation with the extremal weight W dot lambda. So there is some degree. Why is this relevant? Here, the cohomology, the boundary, the Borel-Serre boundary is a space which fibers over the locally symmetric space of the levy, and the fiber is in some sense a symmetric space or locally symmetric space for the unipolar radical. So you have some vibration like this. And so there's a Lorentz spectral sequence which says that this cohomology is the cohomology of the levy with coefficients in this boundary in the cohomology of the unipolar radical. And this, I beg your pardon, is the unipolar radical. And then this Constant's theorem kicks in, and one has to understand while group combinatorics to understand the relevant sheaves, and then what degrees in which I have cohomology. So we have to get into details to sort of add some more. Yeah. So, and those things for GLN prime, things work very well. There's some very nice numerologies involving dimensions of various locally symmetric spaces and cohomology degrees. And in some sense, when I could make that work in some other contexts, we are able to prove theorems. There are all kinds of exotic L functions. So just, here is one, which I particularly like. Take E6, delete that. Now what you see, this is like an E1 orthogonal group. This is like a D5. So here, the levy turns out to be spin 10. Then the corresponding Langlands L function is a degree 16 representation. It's a half spin representation, irreducible representation of spin 10. No one knows anything about these these are very exotic L functions. And then you can ask arithmetic, special values, p-adic interpolation, if possible, and there's an entire story which can. Sorry, and I don't know, I kind of started digressing on that.
I also had a more basic question. Maybe this is a good one to get in. It's like p-adic arithmetic number theories. Basically, every project I work on, I've had to learn a little bit more about algebraic groups. And I've once heard a theorem that you can never know enough about algebraic groups and all this stuff. So for the students, how would you recommend they learn the theory of algebraic groups?
In some sense, what I did in this talk, have a very concrete example in your mind, GL2. If GL2 feels good, then GLN. And try to, there are 3 standard books. There's one by Borel, which has all the information but totally unreadable. There's one by Humphreys, which is quite readable but doesn't go far enough. And I think Springer's book, Linear Algebraic Groups, is just right there. Maybe the first 10 chapters of Springer you read, working out GL2, GLN, the sort of example like this SP2L, these kind of examples. So you have to dirty your hands with examples while reading the general speech. Yeah, people like Borel or Langlands will just talk in all generality. Even harder was like that. He would talk about a reductive group, or he would talk about SL2, not even GL2. And in this, we worked for 10 years before it became this book. The first year was a constant battle between SL2 and GL2. That one I won. I convinced him that GLN is better than SLN. There are many other battles which I lost. Oh, by the way, someone said, Bladen, was it you? So you said you write your L function always as L pi S? Yeah, so this is, so here is a fantastic story. So we are writing this book, okay? So half the battle is with notations. And with L functions, I need some space. So there is the LS pi club, and there's the L pi S club. This is very serious. So then I dug into literature. So Langlands is here. It will make you happy that Devin is here. Tate is here. Jacques, Shahidi, and so on. These people are here. So I made this list. I thought of all the names I could think of who have made big contributions with L functions. I made this table. And it's really, the world was divided, okay? So no one was superior to the quotes, by the way, is here. And harder is here. And I grew up by studying Jack-Langlitz as a student, so I certainly came from there. And this was a constant battle. So then Harder was like, let's go see what Hecker did. And we actually stormed into the library. And Hecker, thank goodness, was here. And Harder was like, no, this is not anything.
Remember, there is no price, so it's both words.
And so Sayre uses some kind of his own notation. So he's neither here nor there.
If it's this maybe in the subscript.
It's in the subscript, yes.
Yeah.
And so in our book, when we talk about automorphic L functions, we use LSPy, and there are certain motivic and cohomological L functions where we use this. And I told the same story to Michael Harris once, and Harris told me that he has caught himself writing a sentence in which he has used both LSPy and LPyS in the same sentence. So he is kind of straddling both.
On your far right board, you switched that to the pi in the induction action.
Yeah, I kind of, as I was writing, it went in my mind that I switched it, but I didn't want to. Yeah.
Wait, so Peter Sarna has a comment about this.
Which is, I haven't told this to Sarna, what it is.
Unitary. So with the automorphic normalization with central half, you have to write LSPy. If it's motivically normalized, you have to write LPyS.
Yeah, okay. So the motivic people certainly are here. And this is all the automorphic people. And so you asked about p-adic interpolation. There is a paper of Harder, which in some sense I want to reconcile that with how the HIDA kind of machinery. Harder's paper is titled On P-adic Interpolation of Coefficient Systems, where, this what you did, the 2, 12, 22, that kind of interpolation of coefficient systems, but in all generality. And so that hasn't been reconciled well yet. So one of my students is going to be working on that. Okay, we should get coffee now. I told you also.
Next 2 minutes.
No.
So I think 11:30 we can take.
Give Raghuram a special thanks.